Okay, so today, as Catalina mentioned, I will talk about a new window opened to explore the universe. As you know, we know the universe mainly through photons with electromagnetic radiation. Last century saw the beginning of the new astronomy based on neutrinos. And now with this discovery, we really hope to have a new tool to explore what we have around us. I want to introduce this topic starting from a very relevant person, very important for the gravitation. He was Newton. He was the first person, the first scientist who built a mathematical framework to describe gravity. This is the famous work where he showed for the first time the ideas. The main idea behind Newton's view can be understood with a very, very simple example, but it is very important because it makes the difference, the passage, we can say, from the previous understanding, which made the clear separation between the terrestrial and the celestial phenomena. They were two completely different worlds, governed by different equations. No, I'm wrong, because the celestial phenomena were perfect. The physics on the earth was connected to humankind, so it could not be compared with what was happening in the heaven. You can understand from this simple example what Newton put in evidence. So imagine you have a mountain on the earth, and you have something, and you throw something. So what happens? It falls down, and this is evident to everybody. Now imagine then you throw stronger this object. What happens? It will fall farther. Yeah. Imagine that you throw even stronger. What happens? It starts falling. It tries to fall. But since the Earth has a finite dimension, it continues falling, falling, and falling. And now we say it starts orbiting the Earth. This is a very simple example, but it is the basic of Newton's idea. And he said, so the moon is falling on the Earth. So it is not only the apple which falls down because it experiences the attraction from the Earth, but the moon as well is falling. Obviously, unfortunately, it doesn't fall on the Earth, but it goes on its orbit, ever and ever. And this was the idea which unified the terrestrial and the celestial phenomena. They are both governed by the same physics. So Newton built the mathematical framework, and you know very well the law which tells us which is the force acting between two masses, m1, m2, at a given distance, d. Now I wrote here equal and opposite. It's wrong. It refers to opposite in the sense that the the vector is pointing in different direction, but it's a bit misleading, no? In the sense the gravitational interaction is always attractive. You should not be confused comparing, for example, with the electromagnetic interaction, which can be attractive or repulsive. And this is one of the biggest difference between the two, the largest difference between the two. Okay, this is always attractive. Gravity always shrinks objects. Okay. This was an extremely successful theory. There was the famous discovery of Neptune, for example, by Leverrier. He was a French astronomer, and his people said he discovered Neptune with his pen, because he made calculations and he understood that there was a missing planet which was not known, but it had to be there in order to explain the motions of all the other known planets. And this was done using the Newton's law. And so the theory was incredibly successful. It could explain many, many unsolved problems. And also conceptually, because it was a great unification theory in some sense. There was, nevertheless, something not convincing in Newton's theory. There was something on the experimental side, because, for example, the orbit of Mercury was not exactly what Newton's equation predicted. There was a difference, you see, in the precession of the perihelion of Mercury. So this is the orbit of Mercury, and it experiences a precession, something like that. And there was some discrepancy between the experimental measurement and the Newton's derivation. But there was also something not convincing on the most, let's say, conceptual side, because you have seen in the previous equation, for example, you do not have the time. What does it mean? That if you put two masses in a given location, they immediately experience this interaction. There is no time in the equation. So the question was, how can a body experience the instantaneous positions of all the other bodies in the universe? How is it possible? You put here something and immediately this effect is experienced by all the other masses, farther, closer, it doesn't matter. Second question is, okay, yeah, we say the moon is falling on the Earth in some sense, but so it means that the moon is experiencing the gravitational interaction, but there is the vacuum between the Earth and the moon. So how is it possible that vacuum transfers anything? And these were really conceptual questions that also philosophers were trying to address. It was necessary, a lot of work by many scientists. Then it was necessary to introduce 1 century later the concept of field, which is not so trivial, but the idea is that when you put to masses, for example, but also for electrical charges is the same, then the condition of the space around them changes. And this is let's say, the motivation. This induces all the physical effects that we see. It is the concept of field, but we do not have time to explain it in detail. Nevertheless, we are now in the at the beginning, let's say, of the 20th century, and there is a guy, Albert Einstein. He knew very well the physics, so he understood perfectly all these problems, conceptual problems. He was very aware of all the progresses of science. For example, the fact that people had been trying to measure the velocity of light and to see if it was depending on the reference frame where you were measuring it. And they really tried to see, to check that the speed of light was not a constant, but the experimental results, nevertheless, were satisfying for them, because they always find the same value. It was something strange. There were strange theories to justify this fact. So Einstein said, I simply considered the experimental facts that I had under my eyes, okay? Without, come si dice, preconcetti, without any bias, okay? Without any bias. And so he could introduce a new theory. At the beginning, it was the so-called special relativity, where he introduced for the first time the concept, very important, the speed of light is independent from the reference frame, it is constant. And this was a very, very important step in the understanding of physical phenomena. For the rest, well, we can say that the special relativity did not differ so much from the Galilean theory, because it was stating that the physical laws are the same in all reference systems moving with mutual constant velocity. But this is exactly the same statement made by Galileo some centuries earlier. The real change was the second step. It was special because it introduced the independency of the speed of light from the reference frame. As you can see, the special relativity was connecting inertial systems, so system moving with constant velocity. So there was an ingredient still missing, the acceleration. What is the acceleration? What is the meaning, the deep meaning of acceleration? And it was something that Einstein considered for 10 years. He needed 10 years to include the concept of acceleration in his theory, and he needed also the support, the help of other people more experienced, for example, in mathematics. One was Marcel Grossman. One was a famous Italian mathematician, Ricci. Ricci Curbastro is the name, Levi Civita. They were very important guys. And Einstein himself expressed his recognition to them for their work on the side of the mathematical aspects of his theory. He made use of concepts introduced by them. Before passing to general relativity, I hope this can work, but I want to show you, this is nice because in everyday life you cannot experience the relevance of special relativity, but it would be very evident to you if you were moving at a speed close to the speed of light, because in this case you would see the objects really deformed when traveling. And for example, this is the effect. There are effects which concern the length and the time. They change. The contraction of this quantity or the dilatation of this quantity. And going to the next step, as we said, special relativity was not the end of the story because reference frames were not included. And this was the question. And the answer, the first, say, hint to solve this problem came from a famous experiment, a Gedanken experiment, a thought experiment, the Einstein's elevator. What does it mean? So you can imagine two different situations here. You have an experimenter, an elevator. This is for him, it's let's say laboratory, his laboratory, no? And then you have a rocket. Now imagine that the elevator doesn't move, and you have a ball in your hand. You lift the ball, what happens? Falls down. Okay, now imagine you are in a rocket which is accelerated upwards with the same g, no? G, what is G? It's the gravitational acceleration, but on the other direction. You are an experimenter, you live in your rocket, okay? This is your lab, in this case. You make the same experiment, you repeat the same experiment, so you have the ball in your hand, you lift the ball, what you see? The ball falls down, because you are going up. The result is the same. And now, what happens? The poor experimenter is not happy in this case, but you cut the wire of the elevator. So now it is falling, freely falling in the gravitational field. The experimenter lifts the ball. What happens? Nothing. Both of them are falling in the gravitational field. And the same is, in this case, happens in this case when the rocket has no acceleration. Obviously, we are assuming that we are far from other masses which can be a source of gravitational interaction. It happens nothing. So, the idea behind this Gedanken experiment is that acceleration is equivalent to gravity. So Einstein understood that solving the problem of acceleration required to understand the profound concept of gravity. What is gravity? And this was another big question. What is gravity? Is it really a force, as Newton was saying? Is something else? The conclusion, after 10 years of work, is that gravity is not a force, but it is a property of the space. And here I wrote space and time, because now you have this new entity which was introduced with the special relativity, space and time. Space can change, but also time can change, depending on the reference system where we measure it. So, if you are moving or not, time is different. So, the new entity is the space-time, the 3 space coordinates plus the time. How can you understand that gravity is a property of space-time? There is another simple experiment. Sorry, the picture is not so good. This is my drawing. You can see I'm particularly good in drawing. These are 2 experimenters. And they make the following experiment. Imagine that they are falling. They are falling in a gravitational field. They don't know there is a gravitational field, but they are falling in a gravitational field, okay? There are 2 persons, 2 experimenters, and they say, okay, let's measure our distance while we are freely moving. So they measure the distance, and since you know when you fall in a gravitational field, the trajectories point toward the center of gravitation. So what they experience? They start at a given distance, they go on, they think to move on straight lines. What happens? They get closer and closer. Yeah, so the distance is changing. So what do they think? You made something wrong. No, it's you. No, it's no. They are physicists. So the experiment is strange. So let's repeat it. So they try and try and try, but the result is always the same. The distance is changing. But they imagine, they assume to live in a flat space-time. And so how can they explain the change in the distance? There is a force, an attracting force among us. They must introduce a force to explain the result of this measurement. But what would happen if the space-time were not flat? The result is described in this picture, because if you can imagine, I didn't draw the experimenters in this case, but imagine that they start here at the equator and they move always. The idea is that they move always parallel to the direction, to the distance which is here among them. They move always parallel because they are moving along meridians. They do not need to introduce an external force. They naturally explain the change in the distance because they have introduced a curved space-time. So, gravitation is equivalent to curving space-time. It means that gravity is a property of space-time, and this was the real breakthrough introduced by Einstein. So it means that you can imagine space-time flat. You have to imagine 2 dimensions. It is not possible, at least for me, to imagine in 3 dimensions. No? So the space-time is a bidimensional membrane, which is flat if there are no masses. But when you put a mass and you put this body on the membrane, this is somehow elastic, so it is deformed by the mass. The mass is warping the space-time. And so when you consider, for example, the motion of a body smaller, its deformation it can be neglected because the second mass is smaller, and you put this small mass, what can it do? It starts moving around the largest mass because the space is no longer flat. So what we say is that matter tells space-time how to bend, and the space-time tells matter how to move. There is this mutual interaction between masses and geometry of space-time. You understand it was really something revolutionary. It was a revolution because Newton's theory had been very successful. It had been able to explain almost perfectly all the known phenomena. And so it was really a step forward with respect to the Newtonian view of the universe. Obviously, any theory needs experimental confirmation. The first one was that it was possible to explain the precession of Mercury, but this didn't convince people really. Another achievement was needed, which was another effect predicted by Einstein theory, because not only, let's say, massive bodies experience the curvature of space-time, but also light should feel it. Why not? It's moving in the space-time, and so it must experience the curvature of space-time. What does it mean? If here you can imagine to have the Earth, where the experimenter lives, and you are looking at a star. Okay, you know the light travels straight. Okay. So you say, okay, the star is in this position. Now, imagine that this is the star, this is the Earth, but there is the sun now in between. What happens to the light ray? It travels here, but at a certain point it starts bending because it experiences the curvature induced by the sun here, this way. And so the experimenter, what can she say? The star is there, because you see the light coming this direction, here. So it means that the position of the star changes. Now the problem was that, you understand, it was necessary to take a picture of some known stars without the sun, and then with the sun. But when there is the sun in between, you cannot see the stars. And so an eclipse was necessary. And there was a famous British astronomer, Sir Arthur Eddington, and he was very convinced about the validity of the Einstein theory. And there is a beautiful movie, My Friend Einstein, which explains very well all the story of these two men. But he wanted to measure this effect, and so he led an expedition to take a picture of this solar eclipse. There was an eclipse foreseen in May 1919. It means 4 years after the publication of the general theory of relativity. And this was the effect that was predicted by the Einstein theory. And so there was this adventure, because it was not easy. He organized 2 sites in the Isle of Principe, which was West Africa, and Sobral, I think, I don't remember what, close to Brazil, I think, I don't remember. But he was very afraid about what? About rain, about clouds, thunderstorm. Anything could happen that could spoil completely this measurement. And then you understand how long he had to wait for another eclipse, total eclipse. So it was really one shot. And he was very wise, because one of the 2 sites, indeed, was, in one of the 2 sites it was not possible to take any picture. So the result, so this is again the effect, and here you can see the difference, no? The theoretical difference between the 2 pictures. So one taken without the sun, the black points are the positions of the stars in the first condition, and then in orange, the position of the stars during the eclipse. Okay, and this is the result of the measurement. This was an article appeared in London Times in November, and you see the title, maybe here small, there is the inset, and you can see maybe these small arrows here, they show the apparent displacement in the position of the stars. So you could really measure the effect predicted by Einstein, and the title is Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown. It was a revolution. And then the explanation of the experiment, which finally convinced the Royal Society, the Royal and Astronomical Societies, about the validity of general relativity. And Einstein became really a very well-known person. There is also this other paper, I think it is very, very nice, Lights All Askew in the Heavens. Men of science, more or less agog, astonished, excited over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need to worry, because stars are not there. No, you do not have to worry. It's an apparent change in the position of the stars. And then it seems that Einstein said that this is something that only very few people can understand. My theory can be understood by very few people at present. A book, and then the paper by Einstein, a book for 12 wise men. Okay. So, again, now we have many confirmation of general relativity. There are many applications. For example, the so-called gravitational lensing. I don't know if you have ever heard about it, but the idea is always the same. Imagine now that you have galaxies here, and then you have the Earth, and then you have another massive object, a galaxy in between. Then you have distant objects, the Earth. So what happens? The rays of these objects here are bent by the presence of the galaxy, and so the result is that the images that you take, they are distorted, and so the galaxy induces a sort of lensing, gravitational lensing, because it changes the pattern of the objects, of the far objects here. It is evident, depending on the relative position between the Earth, the galaxy, and the distant objects, you will have different shapes that can be produced, different images that can be produced. For example, you see this, it is called the smiling cosmos because you have something recalling the famous smile. This is, for example, the simulation of gravitational lensing. You see what happens when a galaxy passing behind a black hole. You see how the image is changing. This is what you can see. You cannot see the black hole, but you can see its effect. And another important application, because many times people ask, okay, but general relativity is a beautiful theory, and so, what is the everyday implication of general relativity? So this is only one example. I know that you all have a cell phone, for sure. And you all have a GPS in your cell phone. Now, if this device did not make use of general relativity, you would never be able to use a GPS, because GPS make use of signals coming from satellites, and the time flows differently in a different gravitational field. And this is a consequence of general relativity. So if the GPS doesn't apply this correction, it doesn't work. They can reach a beautiful precision, you know, less than a meter. If this correction were not taken into account, in a couple of weeks, the position would be wrong by some hundreds of meters. So the effect is relevant in this case. This is an example. 10 minutes, okay. Okay, now so we come to the last prediction that is very important, which is the existence of gravitational waves. They are ripples in space-time, because again, you can imagine that you have a mass and it is static. It bends the space. But if the masses that you consider are moving, then the process is dynamic. And so this membrane sees ripples forming on it, and these ripples, which are ripples in the space-time, they propagate in the space-time membrane, traveling at the speed of light. So in practice, gravitational waves give us information about the presence of masses, how they are moving in the space-time. This is a new prediction. It is very equivalent to, it is worth seeing. It's, I think you can understand better. No, sorry. If it doesn't work, I give up.
According to Einstein, space-time is like a fabric, and what we call gravity is the warping of this fabric by
Can you
a
hear?
massive object, like a star. A planet orbits a star when it's caught in this warped space, like a ball spinning around a roulette wheel. It's an astonishing idea, and it led Einstein to a prediction that when a massive object collides with another, or changes speed or direction, it produces waves in the fabric of space-time. Gravity waves.
Okay, so these gravity waves are produced by accelerated masses. They cannot be produced in the laboratory. Einstein himself made a calculation, and he checked that the amplitude of the waves that you can produce in your lab is too small to be detected. So you need to go to astrophysical objects, and there are different phenomena that you can consider, including very, very strong accelerations. For example, when a star explodes at the end of its life, this is indeed a huge acceleration of a big mass, a supernova explosion, and this can induce emission of gravitational waves, not only of gravitational waves, because there is a lot of light coming in the explosion. There are also neutrinos emitted, a lot of neutrinos. There was, for example, a large a big supernova. It was detected by the Chinese astronomers at beginning of last millennium, and you see a new star. It was so strong that it appeared, as a star, a new star born, like a celestial guardian, and it was so bright that during the daylight, as the polar star is during the night. So they are impressive explosions in the sky. There are also other objects, very, very strange, so-called neutron stars, where the mass is very, very concentrated. They are characterized by huge magnetic fields, and they can emit light, radio waves in this case. When they rotate, they typically rotate very fast, and so they are as a lighthouse, and when they point toward us, we can say this flash of light, and so we can measure them. We know there are many, many in the galaxy, 10 to the 8, 10 to the 9, but since you see the cone, the emission cone of radio light, let's say, it's very narrow. We know only a small fraction, but they can emit gravitational wave. There are many other phenomena. Now here I want to show you some pictures. This is a black hole, so it's the final stage of a very massive star, more than 10 solar masses. I have to correct, this is a mistake. And so a black hole is black, because light cannot escape from a black hole, but you can see the matter surrounding the black hole, which is accelerated, and so it can emit electromagnetic radiation. Or, for example, you can have two very massive objects, two neutron stars, or two black holes as well. They can orbit around a common center of mass, and this movement can induce distortions in the space-time as well, and so they can emit gravitational waves. At the end, since they lose energy because they emit gravitational radiation, at the end they will merge, you see, to form a single object. And so this is particularly interesting because this is what we have measured some months ago. Okay, there are many different types of phenomena. This is, for example, the case of two neutron stars, two pulsars. The neutron star which can emit this light cone are called pulsars, but the phenomenon is very similar. But this is another interesting thing. This is the case of a black hole and a pulsar. In this case, it's a mixed system. So what happens? The neutron star is deformed by the presence of the black hole, and so it's destroyed. The black hole, sooner or later, will eat the neutron star. And so the star is completely destroyed. It falls in the horizon of the black hole with the final emission of a gamma ray burst. I think you have heard about gamma burst. And many other systems, okay? These objects, in particular black holes, can be also very, very massive. They go from some solar masses to millions of solar masses, giant objects which have been proven to exist. What is the signal that we expect? You have seen this is an accelerated motion, and so we expect something which increases in frequency because the two bodies travel faster and faster, and also the amplitude goes up. There were two guys, Russell Hals and Joseph Taylor, who measured an effect very important. They, at a certain point, people didn't know at that time that binary systems, so systems made by two objects, could exist. Nobody had measured. But they were looking for new pulsars. And so they saw a very strange thing. There was a pulsar. A pulsar is a rotating object, and this lighthouse is very precise. It's a precise clock, tick, 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 tick. So you have to measure these pulses at very precise times. But they saw that this pulsar was strange because the pulses were not so precise. They had a modulation, periodical, and they understood that this modulation was due to the presence of a companion object. So the pulsar was not isolated, it was linked to another object, and so it was orbiting around the other object, and so the timing of the pulses was changing for Doppler effect, because the pulsar was getting closer and farther, closer and farther, and closer and farther. And this was the first evidence of a pulsar in a binary system, of the existence of a binary system. Okay. And so they measure this effect because the pulsar is losing energy due to emission of gravitational wave, and so the period is changing. And so they measured over many years, more than 20 years, the period. The period is changing, is becoming smaller because the system is emitting gravitational waves. So these are the experimental measurement, and the line is not a fit, is the result, the prediction of general relativity. And so you see, the agreement is impressive. In fact, I got the Nobel Prize for this measurement. So it was the first indirect evidence of the existence of gravitational wave. What is the effect on a gravitational wave on a real detector? They have not measured the interaction of the gravitational wave with the detector. They've seen the effect on this astronomical system. What is the effect? Well, it's a very peculiar effect because the gravitational wave shrinks the space-time. So if we have a collection of test masses, for example here, the effect of the wave is something like that. You can imagine the wave traveling perpendicular to the plane, and what happens is the space-time is is compressed in the two perpendicular direction, and so the distance between the objects is changing. So you have to measure the distance between two objects of the length of an object. And this is the idea behind the measurement of this effect that was computed in any case to be very, very small, 10 to the minus 18 meters. So we have to measure a change in the length or in the distance of something of the order of 10 to the minus 18. How small is 10 to the minus 18? But, well, if you start from 1 meter, and then you divide, then you divide, then you divide, then you divide again, then here you are at the nuclear diameter, 10 to the minus 15 meter. You have to divide by a factor of 1,000 more, and you get to 10 to the minus 18. So this is the experimental goal that we have to meet. This idea, because the physicists are crazy, because sometimes they really they start something that seems impossible. This man was Joe Weber, and he started everything. The idea to measure the gravitational wave in a lab was introduced by this man. This is the first experiment, which was, say, the progenitor of the Nautilus experiment here in the laboratories. And the idea is that the gravitational wave distorts the space-time and all the objects. And so you have this bar, you have some transducer to measure the movement of the bar. When the gravitational wave arrives, the bar vibrates, and you have to measure the vibration of the bar. And this was the first experiment conceived. Then the concept evolved, and more sophisticated experiments came out. And this is Nautilus installed here, and this is the twin experiment in North Italy near Padua. Then, okay, I don't have time to go deeply because I want to take a couple of minutes to describe the other type of experiment, which is called the Michelson interferometer. Now I have a movie which can explain very well how it works. The idea is that you have a laser which is splitted in two different rays traveling perpendicularly. And then there is a mirror here, the light is reflected back, and it is reflected. This is called beam splitter. It is reflected toward the sensor, and here you measure the interference between the two rays. And so what happens? When the gravitational wave arrives, the distance between the beam splitter and the two mirrors changes. And so the interference, because it changes the time taken by the light to travel, and so the sensor measures a change in the light. And so this is a picture. It's very fast, so it's worth showing it. You see this is the laser which splits, comes back, reaches the photodetector, and when there is the gravitational wave, the light changes. This is the electromagnetic field. It travels at the speed of light in two directions. It's reflected back. It reaches the beam splitter. It goes toward the photodetector, and when there is the effect of the gravitational wave, you can see an alternation of darkness, brightness, and so on. This is the picture of the Virgo experiment. It's located in Pisa. There are now these are huge experiments because the effect is proportional to the length of the arms. These are 3 kilometers long. This is located in Pisa, okay, And then there are different detectors spread around the world. In the US, these are the two LIGO experiments together with Virgo. They are the three largest detectors in the world. This is a picture of the pipe, 3 kilometers long, where the light, the laser light travels. So what? Then I will leave you the slides. This project started some years ago with the goal to measure gravitational waves. This is again the effect, but it is not very clear. You can see the two black holes, for example. This is an animation, obviously. And you see this green wave, they become light, the color is becoming lighter to show that the amplitude is increasing. And also you see the two bodies go faster and faster, and at the end they merge to form a single black hole. And this is what we measured. This is the effect that we measured. Exactly, we measured this signal increasing in frequency and time. And it was measured in February, so some months ago. And in this graph, there is the velocity, for example. In unit of c, the relative velocity. So you can see that these two black holes, each was about 30 solar masses. 30 solar masses. And they had a relative velocity about 0.5 c. So 150.000, so 150,000 kilometers per second. Okay, so they were traveling at an incredible speed, and they merged to form this final object. All this happened in 200 milliseconds. So the system was there from millions, billions of years, spiraling, losing energy, faster and faster, faster and faster. And with our detectors, we could measure the very, very last stage of its life, 200 milliseconds. And I hope, I'm not sure, this is the sound. If we could have heard the sound of this black hole, I don't know if it's working. Because I am at the very end. Come? Bravo. Also, I hope it works. Now you will hear two things. It's the noise, which is always present. And in the noise you will hear something like whoop, whoop. And this is the sound that you could hear. And this is the sampling of the signal to acoustic frequencies, because it is 200 hertz, so it's really an acoustic frequency that you could hear. And then we will hear the same resampled at a higher frequency to make it easier to listen. So, could you hear? Okay, so this is what we measured. This is obviously a very, very important result. We had this tail here missing about the universe. We didn't know this part of the table. Now we have opened at the end, after many, many years, this new window. So you see, 100 years after general relativity. It's incredible. Okay. So I think it's really a new window on the universe. This is the same end that I used the last year. We had not yet seen gravitational waves. We were all confident we would have. And I ended with great science in the next years. And so I repeat the same sentence, but now we are really very proud and happy. We will do that fruitfully. Thanks.
Grazie.